Hi STAT students, let's go over your Unit 5 quiz review for tomorrow. So number 1 says the National Directory of Magazines tracks the number of magazines published in the United States each year. An analysis of data from 1988 to 2007 gives the following computer output. The dates were recorded as years since 1988. Thus, the year 1988 was recorded as year 0. Residual plot is not shown, showed no pattern. All right. So remember that this is your x variable, this is your slope, this is your y-intercept right here. So what is the value of the slope of the least squares regression line? That is 325.39 over 1. And remember, your slope is the change in y over the change in x. So you kind of have to look for the context of the problem here. And we're saying that the years is a result of the number of magazines being published. So for every one, x is years, year, for every 1 year or every year, the number of magazines published increases by 325.39. And don't worry that it's a decimal, that's okay. And of course, that variable, the number of magazines published, wasn't given to us. We had to look inside the context of the problem to find that. So that might happen. What is the value of the y-intercept? All right, there it is. Remember way back and always with linear equations, the y-intercept is when x equals 0. So your y-intercept is 0, 13,549.9. So, when x is 0 and x is the number of years since 1988. So essentially, the initial year, or year number 0, which is 1988, there were 13,549.9 magazines published. All right, down here it says predict the number of magazines published in the United States in 1999. Okay, well, in order to do that, we need to get our least squares regression line. It has not asked us for that yet, but we have all the elements. Y hat equals 325.39 x plus 13,549.9. So predict the number of magazines published in the United States in 1999. This is 11 years since 1988, so x equals 11. And we're going to plug that in. So y hat is equal to 325.39 times 11 plus that 13,549.9, and we will get 17,129.19 magazines were produced in 1999. Okay, D. What is the value of the correlation coefficient for number of magazines published in the U.S. and years since 1988? Interpret this correlation. Okay, so remember up here in the mini tab, we are given the r-squared value. It's right here. But the correlation coefficient is r. R-squared is the coefficient of determination. So r-squared is equal to 0.848. So let's take the square root, of both, and r is equal to 0.921. So that would indicate that there is a strong, and now, before you say positive or negative, when you take the square root, it will always be positive. You need to check the slope. Make sure the R value matches that of the slope. Okay, the slope is positive, so I'm going to keep R positive. There's strong, positive, linear relationship between number of magazines published and years since 1988. If you were wondering about the interpretation of that R squared value, you might need to know that on your test. So if you're wondering, it would be 84.8% of the variation in the number of magazines published can be accounted for or attributed to by the linear relationship with X, which is the number of years since 1988. All right, let's move on to number 2. So the heights in inches and weights in pounds of 6 male Labrador retrievers was measured. The height of a dog is measured at the shoulder. A linear regression analysis was done and the residual plot is provided right here. All right, so cool. We've got the mini tab printout and we've got the residual plot. Is a line an appropriate model to use for these data? What information tells you this? Okay, remember, there are 4 things that lets us know if a linear fit is appropriate. The first thing is we look at the scatter plot. Unfortunately, in this case, we don't have the scatter plot. The second thing we look at is the R and R squared values. Okay, so R squared is 95.3. And so our R value is the square root of 0.953. And that is going to be 0.976. Okay, and our height is a positive slope. We've got the slope across, that's positive, so positive 0.976 is what our R value is. Okay, so I've got a high R squared value, a high R value, and a residual plot that doesn't really seem to show any clear curvature. I might have a curve here, but this dot here kind of throws that off, making it kind of random. There are only 6 data points, so that makes it kind of hard to interpret. But it seems that a line would be appropriate. A line would be appropriate since R and R squared values are strong and the residual plot does not show clear curvature. Yeah, so if this point was removed, I would say there's definitely clear curvature, but since this point is inside the data set, that makes this kind of a little bit more random. I've got some above, some below, and it's kind of just, there's not that many data points, so it's hard to see. But based off the strong R and R squared value, I think we're doing okay. Obviously, we can't look at the scatter plot since we weren't provided that. All right, let's look at B. Write an equation of the least squares regression line. Write the equation in context. Okay, so remember, height is our x, and across from that is our slope. Our y-intercept is negative 13.430, and I don't know what my y variable is by just looking at this table. I have to look at the context. If height is x, then weight is y. So my equation would be weight hat equals 3.6956 height minus 13.430. So there's our equation in context. All right, Dakota is a male Labrador, was one of the dogs measured for this study. His height is 23.5 inches. Find Dakota's predicted weight and Dakota's actual weight. Okay. Height, remember, is an x value. So 23.5 inches, that means x equals 23.5. And remember, on your residual plot is always residuals versus the x. So I have height here. Okay, so I can go find Dakota's residual. It's right here. That's Dakota's point, 23.5. Okay, and the residual for that point, the vertical distance, is 1, 2, 3. Okay, so the residual is, oh, I'm sorry, 3 boxes is 1.5. We're going by 2, so that space is actually 1.5. So y minus y hat equals a positive 1.5 since it's above the line. Okay, I want to know Dakota's actual and predicted weight. Okay, so in order to find his predicted weight, I have to go plug in my x value of 23.5 into my equation. So his predicted weight is y hat equals 3.6956 times 23.5 minus 13.430. And I get out that the predicted weight is approximately 73.446. Okay, so I know the residual is 1.5, and now I know the predictive weight is 73.446. So his actual weight, I can just solve for here by adding 73.446 over. And I get his actual weight was approximately was 74.946. So the line actually underestimated Dakota's weight a little bit, and we know that since the residual was positive. So this was Dakota's actual weight, and this was Dakota's expected weight. And remember, the residual is the vertical distance from the observed point to the expected point, or what we see to what we predict. And so I got that residual here, and I was able to work kind of backwards to find that out. It's really important that you understand the definition of a residual and what it means in order for this problem to make any sense to you. So if you're really confused on this problem, you might want to revisit residuals and what they mean. All right, let's go to number 3. Okay, so now I'm working with actually raw data here. The problem of soil erosion is faced by farmers all over the world. The following data was from a study in Western India. So I'm looking at velocity of wind versus erosion. So we're going to put the velocity in list 1 and erosion in list 2. And we're going to go ahead and create a scatter plot of this data, okay? So put your data in list 1 and list 2. And then you are going to want to follow the following instructions. If you know how to do this on your calculator, skip ahead. You're going to do stat edit. And you're going to enter the data into list 1 and 2. That's the first step. The second step is you're going to hit second stat plot. And you're going to make sure the following things. Only one plot is on. You select the type. That is the first box. There's 6 options. The first box. You're going to select your lists. List 1 is what you want on the x-axis, and list 2 is what you want on the y-axis. Then you're going to hit graph. And then you're going to hit zoom 9. All right. And you want to label everything up appropriately on your graph. I'm going to move this out of the way if you don't need it anymore. Okay, so we're going to have velocity, which is in list 1. This is erosion, which is list 2. And it should look something like this. Something like that, okay? Now we're going to calculate our least squares regression line. Okay, how do we do this? You're going to hit on your calculator. Stat, Edit, and you're going to choose option 8, which is linear regression. And you're going to make sure that you choose list 1 versus list 2. No frequency list. If you want to store the regression equation, you can to see what it looks like. You don't have to, but that's up to you. Okay, so that's what we're going to do right there. 1 second. All right, it says calculate the least square regression line in context, so make sure you do it in context. It's going to look like this. Erosion hat equals negative 282.0 plus 19.851 times velocity. Interpret the slope in context of the problem. The slope is 19.851 over 1, change in y over change in x, recall. So for every 1 kilometer per hour increase in velocity, there is a 19.851 kilogram per day increase in erosion. Your y-intercept is when x is 0. So let's interpret this right here. When wind velocity is 0 kilometers per hour, erosion is predicted to be negative 282.0 kilograms per day. And honestly, your y-intercept interpretation may not always make sense. It may not be realistic because your y-intercept most of the time is pretty far off of the scope of the graph. So it's being extrapolated. So that's okay if it doesn't make sense. All right. You should have your r and your r squared values right there. If you don't, remember you need to turn them on. So if you didn't get your r and r squared values when you hit linear regression, you need to make sure you turn them on by hitting second catalog. Catalog is on 0, and you turn diagnostic on. You need to remember how to do this. Okay, the R value is 0.903, which means there is a strong positive linear relationship between velocity and erosion. Let's do r squared. R squared is equal to 0.816. So this means 81.6% of the variation in y, which is erosion, can be accounted for by the linear relationship with x, and x is velocity. Cool. Now we have to look at our residual plot. It says create a residual plot, and what does it indicate? All right. So right now in your calculator, you should have, in list 1, you should have your x values. In list 2, you should have your y values. List 3, I want my y hat values, so I'm going to plug in my equation, negative 282.0 plus 19.851 times every x value in list 1. And list 4, I want my residuals, which is y minus y hat, list 2 minus list 3. Your residuals are always x values. So my x values are in list 1, velocity, versus the residuals, which are in list 4. You're going to follow the same steps that we did above for graphing those if you forgot, except for now you just make sure you have list 1 versus list 4 rather than list 1 versus list 2. And this is what your plot should look like slightly, or approximately. Something like that. Okay, I definitely would say that there is some slight curvature going on here, okay? So it says, what does the residual plot indicate? Okay, the residual plot shows some slight curvature, which indicates a linear fit may not be best. So this question is just asking just based off of the residual plot, just off of what I see here, okay? Obviously, we could take everything that we see into account if we were asked, is a linear fit appropriate? But that's not what this asked. It just asked for you to interpret that residual plot. And so the key is, if you see a pattern in the residual plot of any kind, pattern or clear curvature 100%, then that indicates that a linear fit might not be best. If it looks mostly random, then you're pretty good, okay? So what you want to make sure is that the residual plot comes out correct and that you stay consistent with your interpretation. If you're saying it's random, the fit is good. If you're saying there's a curve, then that means the fit is not so great. So be consistent above all, and that's that. So if you have any questions, I will be available at lunch today, so you could come see me. Otherwise, I will see you tomorrow. Bye.